With the knowledge of the average molecular energy, we're now ready to study the so-called molar specific heat of an ideal gas. In general, if a system of n moles absorbs an amount of heat dq while its temperature increases by dt, then we can define the molar specific heat C as dq equals nc dt. In other words, C equals 1 over n dq dt. So what is C, the molar specific heat? It is the amount of heat absorbed in order to raise the temperature of the substance by 1 unit while the quantity of this substance is 1 mole. Okay, so it's 1 over n dq over dt. Now, when we calculated the specific heat values before, say for water, water is a liquid. Its pressure and volume hardly changes even as the temperature changes. The same thing cannot be said for gases in general, because when you heat up the gas, you know its volume and or its pressure can change dramatically, right? So we will be more careful about it. Let us apply generally the first law of thermodynamics. The amount of heat dq absorbed by a certain substance equals its change in internal energy minus the work done on the gas. The work done on the gas when the pressure is P and the change in volume is dV, that work is negative P dV. So we have dq equals d internal plus P dV. You see, in order to find dq, not only do we have to know the change in internal energy, we also have to know the next term, P dV. And different processes will have different results of this P dV. For example, is the pressure a constant? Is the volume a constant? Or whatever. If the system undergoes a different path, then the value of P dV could be different. For example, look at one special case. V is a constant, okay? That's an isometric process. V equals a constant. Then, of course, dV is equal to 0, so you don't have to worry about the next term at all, right? You have dq equals dE internal. Okay, this particular dq, we use a subscript V for it. That V stands for the fact that dq is the heat taken in when V is a constant. So what is that equal to? dE internal. We don't have the next term, right? What is that equal to? NCV dt. What's CV? This is the specific heat of the substance with constant volume. Okay, we call it CV. So what is CV equal to? Well, all we have to do is move this n to one side and move this dt to that side. So we have CV equals 1 over n dq dt at constant V. Therefore, it is equal to 1 over n dE internal dt. Okay, so you see, all we need to do in order to find CV is to make sure that we know how to write in E internal as a function of temperature. And then we take a derivative with respect to T, and therefore we get CV. So it's quite simple. Now, let us figure out what E internal is. Using the equipartition theorem, okay, we know E internal is, first of all, if you have a total number of particles is n, okay, so it's n times the average energy per molecule, right? Average energy per molecule. So I can write this as, this n is the number of moles times the number of particles per mole, that's Avogadro's number, and then times the average average energy per molecule. And the average energy per molecule, of course, in general has, you have translational kinetic energy, you have rotational kinetic energy, and you also have vibrational energy in general. The calculation of the E average depends on what kind of gas it is, monatomic, polyatomic, diatomic, and so forth. So we are going to use the knowledge we learned before from equipartition theorem to calculate E average. This will allow us to find D internal, E internal as a function of temperature. The derivative will lead us to CV. So for monatomic ideal gas, the average energy per molecule is only the translational kinetic energy average value. That's 3½ kT because it's 3 degrees of freedom, remember? Okay, so you have n, the number of moles, times Avogadro's number, times 3/2 of kT. You combine Na, the Avogadro's number, with the Boltzmann constant, you get a universal gas constant R, so that's 3/2 nRT. That should be a familiar result. That is for monatomic ideal gas. And then what about diatomic? For diatomic, you should replace that 3 with 5 because there are 5 degrees of freedom. Remember, 2 for rotation. That's in addition to 3 translational motion. So this is equal to 5 over 2 nRT. That's for diatomic We're going to worry about polyatomic a little later. If you have these values for E internal, we can then take a derivative with respect to temperature, and then we can find the value of CV. Okay, so let's see. For monatomic ideal gas, CV, what is that equal to? That is 1 over n ddt of 3/2 nRT, right? And then n cancels. That derivative is, just dt over dt, that's just 1. So the answer is 3/2 of R. Monatomic. Any monatomic ideal gas. Here is the value of CV. It is independent of what kind of molecule it is, as long as it's monatomic. For example, helium, neon, argon, all these are monatomic gases. If we treat them as ideal gas, this is the value of their specific heat per mole. Okay, we know what the value of R is. R is 8.31 in SI system. Multiply this by 3 over 2, and the answer is 12.5 joules per mole per Kelvin. In other words, in order to raise the temperature of a monatomic ideal gas by 1 Kelvin, if it's 1 mole of ideal gas, you have to give it this much energy. That's 12.5 joules. That's what CV means, of course, under constant change, under constant volume. In a diatomic molecule case, CV, all you have to do is to make sure that you change that 3 to 5, right? So the answer is 5 over 2R. And the answer numerically, you multiply 5 over 2 times 8.31, the answer is 20.8 joule per mole per Kelvin. Now, does that agree with experimental values? Okay, there is a table on page 647, table 21.2. Let's take a look. Okay, some monatomic gases. These are real gases, not necessarily ideal. Helium, argon, neon, krypton. Look at these gases. The CV value. Let's not look at CP for now. Okay, just CV. 12.5, 12.5, 12.7, 12.3. These are remarkably close to our prediction of 12.5, even though these are totally different gases. The only thing they have in common is that they're all monatomic. So you see, we have certainly used statistical physics to get down to the molecular root of the quantity called the specific heat. So that is why, even though these gases are very different in terms of atomic structure, we found something in common, something that transcends their differences. It's because we have captured essential physics. Next, let's look at some diatomic gases. Okay, the molar specific heat for constant volume should be 20.8 according to the theoretical prediction. And what are we getting here? For H2, for hydrogen, we get 20.4, nitrogen, 20.8, oxygen, 21.1, and so on. You see, again, these are remarkably close to the value that we're looking for, which is 20.8. Of course, there are some differences because, remember, these are not real ideal gases. Okay, they're not truly ideal. There are some residual intermolecular action. Therefore, they're only close to ideal gas. But it does tell you that the ideal gas serves as an excellent approximation to most real gases. Now, finally, let's take a look at polyatomic. For polyatomic gases, let's look at the value of CV. Let's bring back an old slide in which we calculate the molecular energy for polyatomic gases. All right, for polyatomic gases, we have kinetic energy for translational motion, kinetic energy for rotation. Each has 3 separate degrees of freedom, so that's 3 RT, because it's 6 degrees of freedom times 1/2 RT for each of them per mole, 3 RT, plus vibrational energy. I singled out the vibrational energy. Okay, suppose for now we ignore the vibrational energy. We'll see why a little later. Then the energy, the internal energy per mole for the polyatomic gas will be 3 RT, right? 3 RT. So we have CV equals, the internal energy will be 3 RT instead of 5 over 2 or 3 over 2. So the answer would be just 3R. And numerically, that will be equal to 3 times 8.31 to, that's 25.0 to 24.9, that is, to 36 figures, joule per mole per Kelvin. If we ignore the vibrational energy, ignore the kinetic and potential energy of vibration, now let's see if this value agrees with experiment. You go back to the same table and look at the CV value. Okay, we're looking for 24.9. The actual values for CO2, SO2, water, and so forth. The CV values are now you are getting somewhat different values. You are getting 28.5, 31, 27, 27. They're not that close to this value anymore, but that is somewhat expected because, after all, we ignored the vibrational energy, just as if they don't exist. And given that, we find that this value is about 25, and the real values are about 28 and so forth. It's not that terribly different from that. That means the vibration energy does contribute somewhat, but not a whole lot, right? I mean, if you really count the vibrational energy fully, you have to go back to here. See how much the vibration energy will contribute. This is the kinetic energy of the vibration. Okay, how many degrees of freedom does it have? 3 and minus 6. Let's say we're looking at CO2. Okay, CO2, that's a 3-atom molecule. So N equals 3, right? N equal to 3. So 3 times 3 minus 6, that's 3 degrees of freedom. So we have 3 extra terms. Plus, don't forget, this is only the kinetic energy of vibration. We actually ignore something else, and that is, you can think of vibration as, as if there were invisible springs in between each atom. So that's how the atoms vibrate, right? So you can think of it as each of them is a simple harmonic oscillator as a good approximation. When you look at a simple harmonic oscillator, you don't just have kinetic energy, do you? You also have potential energy due to the spring term. And for each term 1/2 mv squared, there is an accompanying term 1/2 kx squared. Remember that? So therefore, there is an additional amount of potential energy due to the vibration of spring potential, effective spring. So we can actually add another thing here. That is the potential energy U due to the vibration. For CO2, there are 3 terms for kV, 3 terms for UV, so there are 6 terms. Now, if each term has the same average value of 1/2 kT, remember, we got 6 terms here only. We have an extra 6 terms between here and there. Doesn't that mean we have to double the value that we got by counting only translational and rotational energy? Now, that means, if we go back to here, this only counts 6 degrees of freedom, right? But you add 6 extra terms due to vibration. If each term, according to equipartition theorem, contributes exactly the same value, 1/2 kT, shouldn't you get double that value? In other words, the value, the actual CV should be double that figure. It's around 50 joules per mole per Kelvin. What is the actual value? Well, the actual value is very close, much closer to this. The actual value is 28.5. Okay, so what does that tell us? It tells us that the vibrational energy is only partially involved. That is why I singled it out. I did not count here even. I totally ignored vibrational energy. In reality, the vibrational energy is only partially responsible for CV. The majority of that energy does not show up in CV. Okay? To use a term in physics, we say the vibrational degrees of freedom are frozen, or at least partially frozen. So the question is, what is going on here? Why is it that the vibrational degrees of freedom cannot be considered equally as rotational and translational motion? Well, to understand that, we have to go beyond classical physics. Okay, we have now a glimpse into what's called quantum effects. Here's the deal. In classical physics, the energy of a particle can be any continuous value. But in quantum physics, that is no longer necessarily the case. In the case of vibration of molecules, for example, it turns out that the energy associated with vibration of the molecule cannot be just any value. Rather, it should assume only a discrete set of values, in which the energy is quantized. That's what we call it quantum effect. So let's say a molecule, due to vibration, can have this much vibrational energy, can also have that much, that much, that much, that much, and so on. But it cannot have an energy value somewhere in between. Okay, cannot have this much energy. In other words, if a molecule is here, you can give it enough energy so it can jump over there. You can do that. But you cannot only give it that much energy, because that only allows it to go over there, which is not allowed. It simply won't do that. Okay, it can either take all this energy or do nothing. So the question is, how far is this energy gap? How far is this energy gap? Well, it turns out that this energy gap, delta E, is much greater than kT. What's kT? kT is the rough value, it's the order of magnitude of the kinetic energy carried by each molecule, right? I mean, according to the equipartition theorem, each molecule, due to the translation motion, carries a certain amount of energy, 3/2 kT, whatever. The order of magnitude is kT, right? Now, imagine if two molecules collide with each other. If the molecules are complicated entities, they're not monatomic or anything, they're complicated. So then when the two molecules collide, it is possible, in theory, that part of the energy transferred between one molecule to another can be used to increase the vibrational energy of that other molecule which receives the energy. That's in principle true. Okay, in other words, you can receive enough energy from somebody else so that you can jump from here to there. But this will be such a rare event at room temperature, because at room temperature, kT is a lot less than delta E. Delta E is determined by the molecular structure, and it turns out delta E is at least an order of magnitude higher than kT if T is room temperature around 300 Kelvin. So what does that tell you? It tells you that even though molecules can pass energy from one to another due to molecular collision, that energy that's lost or gained by a molecule in a typical collision is around of the order kT, and that is not enough. It is not large enough to close this gap. In other words, it is not enough for this molecule to jump from one level to the next level of vibrational energy. So what did that tell you? It means the vibrational energy, all the levels are here, okay? But they're not, somewhat inaccessible, you see? It's just like you walk stairs, right? Now normally, the stair is small enough so that we can easily walk from here to there, or even take a couple of stairs if we wanted to. But if we have giant stairs like this, let's say this is like a couple of meters, there's no way for us to just walk from this step to the next step. It doesn't mean the next step does not exist. It only means we don't have enough energy to go from this step to the next step. So just effectively as if those steps do not exist, because I can only stay right here. I have no way of going up there. This is why we say the vibrational energy, the vibrational degrees of freedoms are frozen. Okay, because you only stay pretty much at the lowest energy level for vibration. You don't go up through molecular collisions, because the typical molecular collision does not give you enough energy from another molecule to push you up there. So you stay where you are. Therefore, the vibration energy typically is not dependent on temperature. At room temperature, at least, it is not accessible. This is why we have excluded the vibrational kinetic the vibrational energy from consideration. Of course, this is only a qualitative analysis. In reality, the freezing of the vibrational kinetic, the vibrational degrees of freedom is not complete, and it gradually gets defrozen, if you will, as the temperature rises. Because as the temperature rises, kT increases, right? So you have more ability to jump up, okay, through molecular collision. So these levels become gradually accessible. The particles can actually jump up and down, change their vibrational energy through collision. Therefore, it gradually becomes accessible. So the actual value of CV, as you can see, is somewhat greater than 25 joule per mole per Kelvin. That is when we completely ignore molecular vibrational energy. even though that is actually still a good approximation, because at room temperature for most molecules, the vibrational energy is not quite accessible. We can almost ignore it. Okay, let's take a look at a figure in the textbook. That's figure 21.7. What we have here is a diatomic molecule, in fact hydrogen. You know, hydrogen has, of course, translational motion, right? It also has rotation. It's a diatomic molecule. It's got rotation. It in fact also has vibration, because the two atoms in the hydrogen molecule, one is here, one is here, one is there. They can breathe like this, going back and forth. The distance between them can change. That is vibrational. This diagram shows you the actual value of CV, the measured value of CV, as a function of temperature. According to equipartition theorem, the kinetic energy due to the translational motion per mole is 3/2 of R, so that will give you 3/2 R for the value of CV. Okay, but actually there is also rotation going on. It's a diatomic thing, so there are 2 extra degrees of freedom. That will give you 3/2 of R. But you see, at very, very low temperature, like you see 20 Kelvin, 50 Kelvin, around I don't know, 60, 70 Kelvin, very, very low temperature, you don't see rotation appearing. You only see 3/2 kT, even though hydrogen H2 is a diatomic molecule. What does that tell you? It tells you that at low enough energy, low enough temperature, that is, even the rotational degree of freedom is frozen. The translational degree of freedom is not frozen, because the energy levels for translational motion very, very, very close to each other. In other words, look at the stairs that we're talking about. These stairs are so close to each other that even at very low temperature, a typical molecular collision can bump molecules from one stair to another and so forth. So the translational degrees of freedom are available even at very low temperature. The rotational degrees of freedom become available at around room temperature. See, room temperature around 300 Kelvin right here. You have 5/2 R. When you see 5/2 R, that means the rotational degree of freedom are also involved. Now, the vibrational degree of freedom are not involved yet, unless you go to a very high temperature, say around 5,000 Kelvin. That is when you're going to get 7/2 times R. You have an extra 2 times 1/2 kT per molecule due to the vibration. That is why you go from 5/2 to 7/2. Why is that? Because, okay, there is one term for the kinetic energy of rotation, of vibration, right? You have one molecule here, another molecule there. There is relative motion between them. So that's 1/2 mv squared. V is the relative motion speed between these two molecules. It is not the average, it is not the speed of the center of mass, okay? But there's also an equal value of potential energy term, 1/2 k R squared, R being the separation between the two molecules, two atoms in H2 molecule. So each of them has, it's a quadratic term, right? So it's got 1/2 kT. So you got an extra kT, okay, per molecule, or extra RT per mole. Therefore, you have to add another R to its value of CV. So you go from 5/2 R to 7/2 R. But that degree of freedom, vibrational degree of freedom, is frozen, okay, at room temperature, and only becomes accessible at much higher temperature. That's when molecular collisions are energetic enough to actually change the vibrational energy from one level to another in a